So, this is the second class on source coding. In the last class, we have seen why we need source coding and why it is possible to do source coding for most of the practical sources, and we have seen some of the desirable properties of source codes and what we should remember while designing source codes. So, in particular, we have seen that we should design uniquely decodable codes, so that at the destination we can decode the code successfully, and also we would like to have prefix code so that we can decode instantaneously. Then we have seen one particular source coding technique called Huffman Code, and in this class we will do craft inequality, which will give us some criteria for us being able to design a code of certain given lengths. And then we will discuss about optimal codes. There we will see what is possible, how much compression is possible for any source. So, obviously we cannot compress to any amount, any size we want. So, what is the limit? So, we will discuss about the limit of compression, and then we will talk about blockwise source coding. So, we have so far seen that we can depending on the statistics of the source, we can code individual symbols to get compression, but we can also combine several symbols and then encode a block of symbols together. So, that way in fact we will see that we can achieve better compression. So, first we will see what we have done in the last class. We have seen that there are two types of source coding. One is lossless, where there is no loss of information due to compression, and the other is lossy compression, where there is some loss of information due to compression. So, the typical examples of lossless source coding is all the file compression techniques we use in computer, like in Linux we have command compress, and in Windows we use WinZip. So, these are all lossless compression technique, obviously, because we can get the file back from the compressed file. In the lossy compression, the typical examples are the standards like JPEG, MPEG, etc., where speech or audio or video signals or even image signals can be compressed very significantly. So, first we have seen that we should do variable length coding whenever needed. It is not always possible to get good compression using fixed length codes. For example, we have taken this particular random variable which takes 4 possible values with these probabilities, and with fixed length code we can compress the signal, we can represent the random variable using 2 bits, and so the average number of bits per symbol is 2, whereas using this variable length code the average length per symbol comes to be 1.75 bits per symbol, and this is the maximum compression that can be done because the entropy of the random variable itself is 1.75. And we have seen different kind of codes. We have seen what is singular code, where there are possibly 2 same code words, 2 different symbols represented by same code words. In this particular example, this is a trivial example where all the code words are same. So, obviously this code cannot be used to represent the source, because in that situation at the destination we will not be able to recover the values of the signal from the encoded bits. So, the code words should be different, and when all the code words are different, the code is called non-singular code. But even this may not be uniquely decodable when we are transmitting one after another symbols, because when we transmit a sequence of symbols, that sequence of symbols should not be decodable in two different ways. So, that is a further restriction we have on the code. So, we can see in fact that this code is not uniquely decodable in that sense, because if we transmit for example 0 1 0, we do not know whether we have received first 0 and then 1 0, or we have received this single code word. So this code, though it is singular, it is not uniquely decodable. So this code, for example, is uniquely decodable, but even then this code, if this code is used, we may not be able to decode the code instantaneously, meaning by whenever we have received a symbol, we may not be able to decode at that instant. We may need to wait for longer time before we know that, well, this is what this particular bit sequence was representing this particular symbol. So we may need to wait for several more code words to reach before we can decide on a previous code word, and that is not required when the code satisfies another more stringent property called prefix condition. Such codes are called prefix codes or prefix free codes or instantaneous codes because they can be decoded instantaneously. Here no code word is a prefix of another code word. In that kind of codes, the codes can be decoded instantaneously. Okay, so this is to show that this code is not uniquely decodable, and here this shows that this is not prefix code because this code word appears as a prefix of this code word. Okay, then we have seen what is Huffman code. We have constructed Huffman code. So the first step was to arrange the probabilities of the random variable of the values of the random variable in decreasing order like this, and then combine these two probabilities into one and add the probabilities and arrange rest of the probabilities with that new probability in decreasing order again here like this. So we have got 0.3 probability because 0.3 is greater than all these probabilities. 0.3 goes to the top, and we add 0 to this symbol and 1 to this symbol as 2 bits of the code words. Then we keep repeating this process. So whenever we add this, we want to add 0 here, so we add 0 to this symbol, and want to add 1 here, so 1 goes to here, and it goes on. So whenever we want to add any bit to a derived probability, we basically add 0 on the left to all the symbols from which that probability came. For example, this 0.3 we want to add 0 to this symbol. This symbol came from these two symbols, so we have added 0 on the left to both these symbols. So this is how we construct Huffman code, and we have seen some nice properties of Huffman codes. For example, Huffman code is a prefix code. We have seen in fact that in that example at least the Huffman code was a prefix code, and it can be proved that Huffman code will be always a prefix code. And Huffman code is optimum in the sense that for any random variable we cannot design a better code than Huffman code. Huffman code will always give us the minimum average length per symbol. So Huffman code gives us the best compression for any random variable. So this is what we did in the last class. Now in this class we are going to do craft inequality, which will give us a condition for existence of a prefix code for any set of lengths. So if you are given a set of lengths, say I tell you that I want a prefix code with length 3, 4, 4, 4, 4, 4. So there should be 6 code words, 1 should have length 2, 5 should have length 4. Is there such a prefix code? So the craft inequality will answer such question. So it will give us a necessary and sufficient condition. So by checking if the length satisfy craft inequality, you can say whether such a prefix code exists or not. Then we will talk about optimal codes, which will answer this question, that how much can we compress for any random variable. Then we will discuss block-wise source coding. There we will see that instead of coding every symbol individually, we can code several symbols as a block together, and that way we can achieve better compression. So here is craft inequality. It says that a prefix code with code word lengths L1, L2 till Lm, these given lengths exists if and only if this condition is satisfied by these lengths. So if we are given a set of lengths and if we want to ask the question whether a prefix code exists with these lengths, then we need to check only this condition. If this condition is satisfied, we know that this such a prefix code exists. If this is not satisfied, we know that such a prefix code does not exist. So, the proof of this inequality has two parts. One is the so called necessity condition, meaning by we need to prove that that condition is really necessary for existence of a prefix code. So, for that what do we need to prove? We need to prove that any prefix codes will satisfy that condition. So, if we prove that any prefix code satisfies this inequality, then that will tell us that if a set of lengths does not satisfy the given condition, given inequality, then there is no prefix code with those lengths, because any prefix code should satisfy that condition. So, this is what we need to prove in this part of the proof. So, this is the necessity of the condition for existence of a prefix code. Then we will prove sufficiency of the condition. There we will show that the condition, the inequality is really sufficient for existence of a prefix code. So, for that what do we need to show? We need to show that if a set of lengths satisfy the inequality, then there is a prefix code with those lengths. So, that is what is meant by sufficiency, which says the condition, the inequality is really sufficient for existence of a prefix code. So, we will prove in this part of the proof that if some given lengths satisfy this condition, then there is a prefix code with these lengths. So, we go on with the proof of the necessity first. We first represent the whole possibilities for the code words as a tree. So, this is a binary tree. Each node, from each node emanates two edges, one labeled by 0, the other labeled by 1. At every node there are two edges coming out of this, one is 0, the other is 1. So, this tree goes on even after this. We have drawn only till the 4th level, 1, 2, 3, 4, 4th level, and this tree actually goes on. Now, in this tree every possible code word is present. For example, this node represents a code word 0, 1. This node, for example, represents a code word 0, 0, 1. So, this is 0, 1 code word, this is 1, 0, 1 code word. So, you take the path from this origin node to this node, you see all the bits you come across, and those bits give you the code corresponding to that node. So, all the possible code words are represented by nodes in this particular tree. Okay. Now, what does prefix condition signify in terms of this tree? So, our code word, our code, whatever code we are going to design or whatever code we have actually is a subset of all these nodes. So, it is our code is basically a set of nodes from this tree. So, we are given a, so this is recall that we are given a code and we are trying to prove that that code must satisfy the inequality given by the Kraft inequality. So, if suppose this is a code word in our code, this node is a code word, that is 0, 1 is a code word in our code, then we know that all these nodes cannot be code words in our code, because what is the code word corresponding to this node? It is 0, 1, 0, of which 0, 1 is a prefix. So, if this is a code word, this node cannot be a code word. So, any node which is coming after this node, which is originating from here, those nodes cannot be code words if this node is, because this node will be prefix of all the nodes coming out of this node. So, all these nodes are disqualified as code words if this node is a code word. So, 0 1 0 0 1 0 this node, 0 1 1 0 1 1 this node, then 0 1 0 0 0 1 0 0. So, this node, this node, this node and this node, all these 6 nodes are disqualified as code words if this is a code word. And not only these are disqualified, these nodes are also disqualified, because this node, for example, this is the node corresponding to the code word 0. This node cannot be also a code word if this is a code word, because then this will be a prefix of this code word. And since our code or given code is a prefix code, this node cannot be a code word. So, if this is a code word in our code, this node and all these nodes cannot be code words. So, these nodes are disqualified whenever you have this node as a code word. Okay. Now, consider a code word C of xi. Xi is the value of the random variable of which C is the code word. So, C of xi is the code word for xi, and suppose it has length li. Okay. Now, we also assume that, so we are given the code. Now, we have all these lengths L1, L2 till L capital M. Now, out of these lengths we have a maximum length. So, we need to expand the tree only till that level, L max, the maximum length. So, till that level we need to expand the tree. Now, after we expand the tree that much, we consider each code word. So, each code word has length less than equal to L max. So, each code word will be present in that tree before that level L max. So, it will be one node from the tree. Now, if we take that node is a code word. So, that node disqualifies some other nodes as code words. So, it will disqualify in particular some nodes at the maximum level. For example, if this is a code word and we have expanded the tree till here, 4th level, suppose our L max is, the maximum length is 4, then we have expanded the tree till the 4th level, and this is a code word, then it will disqualify 4 nodes at the maximum level, 1, 2, 3, 4. So, we will count all these nodes at the maximum level that are disqualified by every code word. So, we will take one code word, we count the number of nodes at the maximum level which are disqualified by that code word. So, how many code words will be disqualified at the maximum level by any code word? If its length is Li and the maximum level is L max, then the difference between this level and this level is L max minus Li. So, the number of nodes that are disqualified, that are coming out of this node here, will be 2 to the power that, because if the level difference is 1, if you go 1 level from here, there are 2 nodes. If you go 2 levels from here, there are 4 nodes, 2 to the power 2. If you go 3 levels, there will be 8 nodes. So, you see the difference between this length and the maximum length. 2 to the power that L max minus Li is the number of nodes at the maximum level which are disqualified by this node. So, if we now count all the nodes at the maximum level that are disqualified by different code words, so let us see what happens. Now, the number of descendants here of Ci of a given code word at level L max is 2 to the power L max minus Li, as we have already observed. Now, we count these numbers for all the code words, and we know that if one code word disqualifies certain nodes here, another code word, suppose this one is a code word, then this will disqualify some other nodes, and these nodes cannot have any common node, because this is a prefix code. This node, if only it was here or here, they could have common descendants. here. So, they will be all different. So, the descendants of this any other code word will be different from descendants of this code word. So, the total number of nodes at the maximum level that are disqualified by all the code words will be simply the sum of such numbers. So, descendants are disjoint for different I. So, for different code word the descendants are different. For example, if this is a code word, this set is different, disjoint from this set. They will intersect only when this node is somewhere here or here, and we know that this code is a prefix code, so that cannot happen. Okay. So, considering all the code words, what is the total number of nodes at the maximum level that are disqualified? It is the sum of 2 to the power L max minus Li for all i's. And we know that the total number of nodes at this level itself is 2 power L max. So, this number must be less than equal to this total number of nodes at this maximum level. So, we have this inequality. This inequality must be satisfied by any prefix code. So, remember where we use the prefix condition, we have used it to conclude that all the descendants of one code word will be disjoint from all the descendants of another code word. So, if these two are code words, their descendants will be disjoint, because this is prefix. No one is in the path of another. So, this node cannot be here or here. So, there the descendants will be disjoint. So, we have used the prefix condition there. So, the summation is less than equal to 2 to the power L max. Now, if we divide by 2 to the power L max both the sides, left hand side and right hand side, then we get the Craft inequality. So, we have this inequality. Now, dividing by L max both sides, we get summation 2 to the power minus Li is less than equal to 1. So, we have proved the necessity condition. Here we have shown that any prefix code must satisfy this condition. So, we have proved any prefix code must satisfy this condition. So, remember again, the necessity, proof of necessity requires, it needs to be shown that the condition is necessary to be satisfied by any prefix code. So, we have proved that any prefix code must satisfy that. So, we have proved the same thing. We have proved that that condition is really necessary for any prefix code. Okay. Now, we go on to the proof of sufficiency. Again, we use this tree, and we are now, remember what we are going to prove now. We are given these lengths, and these lengths are given in such a way that they satisfy the Craft inequality. So, we are going to now show that there is a prefix code with these lengths. So, then what will it prove? If I show that, it will prove that this condition, the Craft inequality, is really a sufficient condition for a prefix code to exist with those lengths. So, in the previous part we have proved that a prefix code must satisfy Craft inequality. But now we are going to prove that if a set of given lengths satisfy Craft inequality, then there is a prefix code with those lengths. So, this condition is really also sufficient for any prefix code to exist with those lengths. So, we now try to prove that. So, we first arrange the lengths in increasing order, and we are in fact going to construct a code which will have these lengths. So, these lengths are given to us, and it is told to us that these lengths satisfy Craft inequality. Then we are going to show that there is a prefix code. So, how will we show that? We will show that by actually constructing a prefix code. So, first we arrange these lengths in increasing order, then we take the first length. So, how do we go about constructing a prefix code? As below. So, we take one by one, we construct one by one code word. So, we take I equal to 1 to m, So, we need to construct m code words. So, we take the first length. So, remember that we are going to pick code words from this tree. So, we will expand the tree till the maximum length, that many levels, and then L1 is the minimum of this. So, we take that code word will be at the lowest level, on the leftmost level, somewhere here. So, we will take the first node from top at level L1. So, suppose L1 is 1, what will we do? We will go to the first level. At first level there are 2 nodes, we will take the first one from top, this one. If L1 was 2, we will go to level 2 here, 1, 2 here. So, at level 2 there are 4 nodes, we will take the topmost, this one. So, we will take the first node at level L1 as the first code word, that will have the minimum length. Then we will, so this will disqualify all the code words here, and this will disqualify all the code words here also. But we are not going to pick any code word from this anyway, because any code word here before this level will have smaller length, and we do not have any smaller length than L1. So, we do not need to construct any code word of length less than L1. So, these nodes are not of our interest, these are disqualified by this node, but we are not going to pick any code word from here anyway. Okay, so, this node disqualifies all these nodes at the later levels. Then we will pick L2. L2 may be equal to L1 or may be greater than L1. So, if it is equal to L1, we will take the next node available at this level. So, this one. So, obviously, it will disqualify some other nodes, they will not intersect with this. So, and this will not be a prefix of this, and this also will not be a prefix of this node. And if this L2 is greater than this, then we will go to that level, L2 level. So, suppose it is 3, L1 is 2 and L2 is 3, then we will go to this level and then choose the first node available. So, what do we mean by the first node available? Remember that some nodes at this level might be disqualified by already chosen code words. For example, if we have chosen this code word, then this has disqualified these 2 nodes at level 3. So, we cannot choose this node as the next code word. So, we choose the node at this level that is available, first node that is available, that is not disqualified. So, we take that and we keep doing that. This will disqualify these 2 nodes, and then again we take the next code word similarly. So, where are we using the condition given? So, that condition is actually telling us that there is some node available at least. Suppose at level 3 you observe that there is no node available after taking these 2 code words, there is no node available at level 3 or for length L3, at level L3 there is no node available. So, what do we do then? Well, then we cannot choose another code word, but this condition will guarantee that there will be some node available. How? So, that is as following. Remember that if there is no node available, then there will not be any node available at the maximum level as well. If all the nodes, if there is some node available at the maximum level, then there will be something available before also, because if this is available, then this will also be available. So, now keep counting the nodes that are disqualified at the maximum level by already chosen code words, and while we do that, we can check that there will always be, till we finish, there will always be some nodes available at the maximum level. So, this will guarantee that there will always be code words available to be chosen till we finish. So, this will give us some construction of a prefix code. So, what we have done is, to prove the sufficiency, we have taken a set of lengths which satisfies this condition, and if it satisfies this condition, then we have shown that there is a prefix code with these lengths by construction. So, we have proved that this condition is sufficient for existence of a prefix code. So, here are some comments about Craft inequality. So far we have proved Craft inequality. We have proved that Craft inequality is really necessary as well as sufficient condition for existence of a prefix code. If a set of given lengths is, if a set of lengths satisfy Craft inequality, then we have shown that there is a prefix code with those lengths. So, the condition is sufficient, and also we have shown that if there is a prefix code with certain lengths, that must satisfy the Craft inequality. So, it is necessary also. So, Craft inequality satisfies necessary as well as sufficient condition. Now, here are some more comments about Craft inequality. Craft inequality also holds for uniquely decodable codes, which means that so far we have seen that Craft inequality is necessary and sufficient condition for existence of a prefix code. So, it does not guarantee that it is also necessary for existence of a uniquely decodable code. It is sufficient certainly, because if a set of lengths satisfy Craft inequality, we know that there is a prefix code with those lengths. So, if there is a prefix code, that prefix code itself is a uniquely decodable code as well. So, Craft inequality is certainly a sufficient condition for existence of a uniquely decodable code also, that is trivial. But that does not mean that it is also necessary. It may happen that a uniquely decodable code exists even if the Craft inequality is not satisfied. Can that happen? So, this comment says that it is really necessary even for existence of a uniquely decodable code. So, this in turn means that whenever there is a uniquely decodable code with certain lengths, there is also a prefix code with those lengths. How? Because if there is a uniquely decodable code with these lengths, then we know that Craft inequality is satisfied by these lengths, and so there must be also a prefix code with these lengths. So, whenever there is a uniquely decodable code with these lengths, with certain lengths, there is also a prefix code with the same lengths. So, this tells us something interesting. It tells us that we should never use a code which is not prefix code, because whenever we are using a code which is not prefix code, but it must be uniquely decodable, of course, because we need to use it for practical purpose. So, we need to be able to decode successfully. So, whenever we are using a code which is uniquely decodable but not prefix code, then we know that there is a code with the same lengths which is also prefix. So, why not use that prefix code itself instead of using the uniquely decodable code? So, this tells us that we should always use prefix code instead of using simply uniquely decodable code. Okay. Now, so what does equality mean in the code? So, if the Craft inequality is satisfied with equality by some lengths, so we are given a set of lengths, and the Craft inequality is satisfied with equality for these lengths, meaning by both the left hand side and left hand side becomes equal to 1 for those lengths. Then what does it mean? It means that at the Lmax level of the code tree, all the nodes will be exhausted, all the nodes will be disqualified after you choose all the code words. No node at the level Lmax will be left free after you choose all the code nodes, code word nodes. Okay. Now, we go into optimal code. So far we have seen that craft inequality is necessary as well as sufficient condition for existence of a prefix code as well as for existence of a uniquely decodable code. Now, we have also seen that we have also seen in the previous page that equality in the craft inequality means that all the nodes at the code tree at level L max, the maximum length, will be disqualified after you choose all the code words from the code tree, all the code words in your code. Okay. So, now let us go ahead to the next topic. We will now discuss on optimal code. So, we will try to answer the question how much compression is possible. So, we are given a random variable, we know the statistics of the random variable, how much can we compress the random variable. Okay. So, first of all we will define what is called optimal code. We have already seen, we have already described Huffman code as an optimal code. So, what is meant by optimal code? It simply means that a code for a random variable x is optimal if there is no code for the same random variable with smaller average length. So, this code achieves the minimum average length that is possible to achieve for that particular random variable. So, that is what is meant by optimal code. That means that particular code will give us the maximum compression on average, okay, for that particular random variable. Okay. So, now we will denote the average length of an optimal code as L from now on. So, remember that L is not the average length of any given code, it is the, it will denote the length of an optimal code. So, this length will be the minimum achievable length by all possible code words, all possible codes. So, here is a very interesting result and very useful result about optimality. It says that the minimum achievable length for any random variable lies in between these two limits. So, we have previously in information theory you have seen that this Hx denotes the entropy of the random variable x, is basically the average information content in the random variable. So, and we have also seen that Shannon's source coding theorem says this is the minimum length to which a source can be compressed, but that will require block wise encoding, as we will see later. But if you do encoding symbol wise, if you take every symbol individually and encode it separately, every symbol independently, then what is the best you can do? That best is given by this theorem, that best, the minimum average length will be in between these two. It is not always possible to achieve this. So, this is the minimum. This may not be possible to be achieved for any random variable. In general, it is possible to get a code which will give us average length less than hx plus 1, but of course, this cannot be less than hx because of source coding theorem. Source coding theorem says it cannot be less than hx. So, it is in this range. So, from here we can say that Huffman code's length will be certainly in this length, in these two limits in between, because it is an optimal code. So, we will prove this theorem, So, while proving this, we will prove first that L is greater than or equal to hx, and also we will prove that L is less than hx plus 1. So, there are two parts. So, when we try to prove that L is greater than or equal to hx, we will not actually prove that optimal length is greater than or equal to hx. We will prove that any code's average length will be greater than or equal to hx. So, you give me any code for a random variable, I can show that it will have average length greater than or equal to hx. So, it will be also true for optimal codes, because it is true for any code. So, we will prove that part for any code, that is L is greater than or equal to hx, and then we will prove that L is less than or equal to hx plus 1, and here we will prove for the optimal code, because if you give me any code, it need not have average length less than hx plus 1. It may be a very lousy code. So, we will prove that there is a code, at least one code, which will have average length less than hx plus 1. So, the proof will be in two parts. So, the first part, for any uniquely decodable code, the expected length is greater than equal to hx. So, we are given a uniquely decodable code, we will prove that its length must be greater than equal to hx. So, first we add all these quantities. Remember, this quantity is basically the left hand side of the craft inequality. This is represented by z. Because it is uniquely decodable, we know that this must be less than equal to 1, because craft inequality is also satisfied by uniquely decodable codes. So, this is less than equal to 1. Now, we will also denote by qi this quantity 2 power minus li by z. So, this z is the summation of all such 2 power minus li's, and we take the ith one here, this is qi, this by the summation of 2 power minus li. So, what is the summation of qi's? Summation of qi's will be equal to 1. So, it is like a probability distribution, probability mass function qi. So, we already have probabilities pi for the random variable that are known. Now, we construct another mass function qi this way from the lengths of the given code. Okay. Now, this is a known equality, we will not prove, but we will assume this, that summation pi log 1 by qi for any qi, in fact this is not only for this, any qi satisfying summation qi equal to 1, this is true, that summation pi log 1 by qi is greater than equal to summation pi log 1 by pi. So, if you replace pi by qi here, so this you know to be the entropy, right, but if you represent this pi by qi, this quantity will increase, that is the inequality. So, and also this equality is satisfied if and only if pi is equal to qi. So, this side will be equal to this side only if pi is equal to qi. Okay. So, this is a very important inequality, and we will use this to prove this theorem. So, what is the length of the code? Average length of the code, it is defined as summation pi li, the average length. So, this is equal to summation pi, and then li can be now replaced by this quantity. So, how do you get this? This is basically you can get from here. So, what is li? Li is 1 by qi will be 2 to the power minus. So, z times qi will be equal to 2 to the power minus li. Okay. So, one can show that li can be expressed in this form. If we replace li from here, we will get this. Now, here again we will use this inequality first. We will know that this quantity is greater than equal to this quantity. So, we replace this by p. So, this is less than this quantity from here, and this log z is as it is here. Okay. Now, this is again greater than equal to hx, because what is log z? Z is less than equal to 1 from craft inequality. So, log z is less than 0. Because log z is less than 0, minus log z is greater than 0. So, if we remove this, something greater than 0, it will decrease. So, this quantity is greater than equal to simply this quantity, which is hx. So, we have shown that this average length of any uniquely decodable code is greater than equal to hx. So, we will just repeat again. So, here we have z, which is the left hand side of the craft inequality for the given uniquely decodable code, and qi is constructed this way, and we use this known inequality. Then we replace this li from here, we get this, and from here we use this inequality. So, replace qi by pi here, and then log z is less than 0 can be used to show that this is greater than equal to hx. Okay. So, this is proved, but there are some things to be observed in this proof. that is, when is this equal to Hx? When can we achieve the maximum compression? So, that can be seen from the proof itself, that what are the things that is to be satisfied to get equality in this inequality. So, what are the things that is to be observed? First, log z should be 0. So, that means craft inequality should be satisfied, this should be equal to 1. So, craft inequality should be satisfied, and then pi should be equal to qi. So, Li, the length of the code, should be equal to log of 1 by pi. So, these conditions will suggest that how to design good code, because to achieve a good length, small length, these conditions should be satisfied. The craft inequality should be satisfied with equality. We should try to achieve as near 1 as possible, this quantity, and also length should be almost equal to this to get good code. Then we will prove that there exist codes with LCX less than equal to Hx plus 1. So, we will construct a code which will have this less than equal to this length. First of all, we will define the lengths. Let us define this way, that Li is equal to the ceiling. Ceiling is the minimum number which is greater than, minimum integer that is greater than this number. So, if this number is 2.5, the ceiling will be 3, the next integer. So, define this length this way. Then we know that this, we can check that these lengths will satisfy craft inequality. So, this summation will be equal to this summation, Li is replaced by this, and this will be less than equal to, if you remove the ceiling, what will happen? If you remove the ceiling, this quantity will decrease. So, minus of this quantity will increase. So, 2 to the power that will increase. So, this will increase. So, this is less than equal to this, and this is 2 to the power minus log 2 1 by pi. So, minus log 2 1 by pi is log 2 pi. So, 2 to the power log 2 pi is simply pi. So, summation pi is 1. So, this is less than equal to 1. So, it satisfies the craft inequality. These lengths as derived this way satisfy the craft inequality. So, there is a code, prefix code with these lengths, and for this prefix code, what is the average length of this prefix code? It is summation pi Li, and this is less than equal to this quantity plus 1. So, 2.5 ceiling 3 must be less than equal to 2.5 plus 1. So, similarly, this is ceiling is less than equal to this plus 1. So, now when you take summation, you get this is less than equal to Hx plus 1. So, there is a code which there is a prefix code which satisfies this condition, which achieves this length less than equal to Hx plus 1. So, the corollary of this theorem is that Huffman code has average length less than equal to Hx plus 1, because it is optimal code. Okay. So, we have discussed craft inequality, and we have discussed craft inequality, and we have discussed what is optimal code and how much is possible to compress for any random variable. And so, we will just see what we have done in this class. We have first seen what is craft inequality. We have seen that this is the necessary and sufficient condition for existence of a prefix code. We have proved the inequality in two parts, necessity and sufficiency. So, this is necessity condition, and so we have proved that any prefix code should satisfy this condition. So, that this condition is necessary, and then we have proved that this condition is also sufficient in a sense that if some lengths satisfy this condition, then there is a prefix code with these lengths. So, we have seen that the craft inequality is also true for uniquely decodable codes. It is necessary as well as sufficient for existence of uniquely decodable codes also, and that meant that if there is a uniquely decodable code with a set of lengths, there is also a prefix code with those lengths. Then we have seen what equality means in craft inequality. Then we have seen a very important result about optimal code. It says that the optimal length, average length of a code for any random variable will be in between these two. So, any code's average length will be greater than or equal to hx, and there is a code with average length less than hx plus 1. Okay. So in this class we have done craft inequality, and we have discussed about Huffman. We have discussed about optimal codes. We have seen that Huffman codes satisfy the optimality condition, and we have some exercises. So, these are some exercises we will solve in the next class, and the topics which we have covered in this class can be found in the same reading text we have given in the last time, that is Thomas and Cover and McKay. And we will do in the next class Shannon-Fano-Elias code, that is also called arithmetic code, and then Lempel-Jeev code. These codes are very different from Huffman codes. We will see in detail in the next class. So, we have done in this class craft inequality, optimal codes. We have not done this blockwise source coding, we will do in the next class, and we will also do Shannon-Fano-Elias arithmetic code and Jeev-Lempel code in the next class.